Hey everyone, in this video I'll be covering Stoke's theorem and we'll be verifying it using line integrals. So I'm going to go ahead and get started. So we have the surface that is z, it should be z squared, equal to x squared plus y squared, and it's bounded by c1 and c2, where at z equal to 1 and z equal to 2. So where these things are missing, but oh well. And for part A, we need to, for C1 and C2, find the direction, the correct direction for where we need to go for the to the side of the pathway. And there's a couple ways to do it to help you figure it out. What I typically do is I think of I'll assign an arrow to the outside or to the surface, and it has to go away from the surface. So this arrow is going away from the inside of the surface, because if you look down at this in the XY plane, looks like this. The arrow is looking like this. But it's on the outside and it's going down and away from the surface, the inside of the surface. So if it's going down, then that would dictate your direction by using the right hand rule. So if you're pointing down, so it goes into the paper, so like it goes into the page. Use a little, let's say use a little X to go into the page. It's like the back of an arrow. That means you'll be doing a clockwise motion. And then for the other part, since the outside for the C2 is right here. So this is the outside for C2. C1. Our arrow has to go towards in here. Goes inside this region right here. Redraw it. So that means your arrow is pointing upward. So yeah, so you'd be going in a counterclockwise direction. So that's the way I do it typically. But the way that Dr. Ralston likes to explain it is the little man. Pretend you're a little person. Don't want to discriminate gender. So if you're a person walking on here, so I'm going to draw a little person right here. Your left hand needs to be over the surface. So if your left hand is over the surface, and your right hand needs to be outside the surface. So it needs to. This is what dictates your direction. So if your left hand is on the surface and your right hand is off the surface, then you can go around. Then like that will decide your direction. So, that means you have a person right here. He's gonna walk around in the, like I said before, clockwise direction for C1. Then for the bottom, you can draw the same person. Doesn't matter which side you pick to. It just needs your right hand and left hand need to be on the same place. So left hand needs to be over the surface. Right hand needs to be outside the surface. So if you're doing that, then you're going to go the other direction, which is counterclockwise. So now we know our directions, and sorry if I can explain it the best way. It's kind of hard to explain this concept without showing some like hand motions or 3D, like some sort of three-dimensional explanation. But I'll go ahead and start getting into line integrals. So we're just going to start with C1. C1 is x squared plus y squared equal to 4 when z equals to 2. So dz would equal 0. And they prompt you to do this, so you're probably going to have to do this in polar, by the way. So, or in all sorts of theta. So x would equal r cosine theta, which r in this case would be 2, since we have x squared plus y squared equal to 4. So that means r squared equal to 4, r equal to 2. So x would be 2 cosine theta. dx would be negative 2 sine theta. d theta. And don't forget those d thetas, they'll mark off for that for sure. And then you have y, which is 2 sine theta d theta. Sorry, not d theta. Then dy, would be 2 cosine theta d theta. Now we'll go ahead and plug into this integral, which would be mdx plus ndy plus pdz. To remember this, it's like f dot dr. And then where m and p are assigned from these values. So you can say it's equal to the integral of 2yz dx plus n dy, x dy plus xy dz. So now we substitute, and this thing kind of prompts us to do all of theta. So we can go ahead and solve for, and go ahead and substitute everything into b in terms of theta. So this part right here will go to 0 since dz equals 0. Then we plug in for 2yz and dx. So we're already given z as 2, so this means the integral would be 2 times the z times 2 times y, which is 2 sine theta, times dx, which is negative 2 sine theta d theta, plus x, which is 2 cosine theta, times dy, which is 2 cosine theta d theta. All right, we'll go ahead and simplify this down in the next line, and we'll start evaluating it. So it would be negative 16 sine squared theta plus 4 cosine squared theta d, and all this times d theta. So we have to figure out what our limits are for this. So our limits are going to have to be the same within the same direction that we chose for our C1 and first C1. So since we chose clockwise, and I drew it down here, it's clockwise, we're really going to start off here and go all the way around. So we're going to go from 2 pi to 0 instead. We're starting after 2 pi and going to 0, so it's going to be 2 pi to 0. Make sure I did this right. Yep. 2 pi to 0. And then we need to substitute in for sine squared and cosine squared. So I would suggest the halving of formula. So halving of formula would end up being so this would be from 2 pi to 0 of, and so the halving of formula for sine and cosine is 1/2 1 plus cosine 2 theta for cosine, and then it's 1 the 1/2 sorry, blanking right now. 1/2 1 minus cosine 2 theta for sine squared. So I'll just go ahead and do it. So we'll have negative 16 here. Actually, I'll go ahead and multiply throughout. No, never mind. I'll just leave it like this. So it's going to be 1/2 times 1 minus cosine 2 theta plus 4. This is the cosine part, 1/2 1 plus cosine 2 theta, and all this times d theta. So simplify this down a little bit. 2 pi to 0 still. Then we'll have negative 8 plus 8 cosine 2 theta plus 2 cosine 2 theta. And then I'm going to go ahead and make this 10 theta. Since we have 8 theta plus 2, 8 cosine theta, 8 cosine 2 theta plus 2 cosine 2 theta. So I want to combine them. And I want to go ahead and combine this negative 8 and negative 2, so it just comes to negative 6.
So then this, so we integrate this. Don't forget my d theta. So then this would equal negative 6 theta plus 5 sine 2 theta from 2 pi to 0, which equals 6, 0 minus 2 pi plus 5 of sine times sine 0 minus sine 2 pi, which this would just equal 12 pi. Sorry. Oh, sorry, I forgot my negative here. This would equal, yeah, 12 pi. Again, this because this will go to 0 and this will go to 0. Actually, sorry, that should be 4 pi anyways, but still, it's 0. So I've got 12 pi for C1. Now for C2, it's the exact same thing. So we have 0, 2 cosine theta, negative 2 sine theta d theta, y is 2 sine theta, dy is 2 cosine theta, d theta. So everything's the exact same thing. The only difference is we're choosing different limits. And R is different this time. So instead of it being 1, 2, it's a 1. My bad for that confusion. Jumped the gun. So since it is x equals r cosine, y equals r sine, r in this case is 1 because we're looking at x squared plus y squared equal to 1, where z equals to 1, so r would equal to 1. So it's literally the exact same thing. The only difference is now is that instead of it just being 16 and 4, it would be you can divide that by factors of 2, by the number of factors of 2 that you would have. So I'll just go ahead and show you. You'll be able to see it. So same thing, integral of m dx plus n dy. So it's going to be 2y z dx plus x dy. I'm not even write the x, y, dz is still 0. So then this would equal the integral, so it would be 2 times y, which is sine theta, z, which is 1, so I'm not going to include that, plus times dx, which is cosine theta, d theta. Sorry, blanking out. Sine theta, d theta, plus x, which is cosine theta, dy, which is cosine theta, d theta. Whoa. I think I accidentally hit the page down button. So then we can simplify this down to being 2 sine squared theta plus cosine squared d theta, theta, d all times d theta. And now our limits, since we're going counterclockwise instead, it'll be from 0 to 2 pi. So because we're going the opposite direction as before. So now we can we'll substitute and integrate again, like we did before, with just different coefficients. So 0 to 2 pi and it would be 1 plus cosine 2 theta plus 1/2 plus 1/2 cosine 2 theta. Sorry, yeah. Oh man, I messed up again. Negative sign here. So this is a negative 1. Oh, sorry for these little mistakes. I don't know what's going on with me right now. I think I just want this to be over. So now, go ahead and combine all these things, these terms. So it equals from 0 to 2 pi of negative 1/2 plus 3/2 cosine 2 theta d theta. and then integrate. It would be negative theta over 2 plus, I don't know if I heard that, but that was just firework, plus 3 over 4 cosine 2, oops, sorry, plus sine 2 theta. We're going from 0 to 2 pi. This sine's still going to go, this sine term's still going to go to 0, so I'm not even going to worry about that. So it's going to be 2 pi minus 0 times negative 1/2, so negative 1/2. 2 pi minus 0, which equals pi, negative pi actually. Which makes the integral for c 12 pi minus pi, which equals 11 pi. Alright, now onto this part. For the surface integral, del f, del is del across the force. So del just being the partial with respect to x, I plus the partial with respect to y, j plus the partial with respect to z, k. We're going to start with our force, which is our mi plus nj plus pk. So this would be partial of x plus partial of yj plus partial of zk. With our force, I think it's 2yzi plus xj plus, what is it for k? xyk. All right, so we cross this. We're going to do I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And we'll have 2yz x, xy. So looking at the I term, it's going to be partial of xy with respect to y minus partial of x with respect to z minus j times partial x y with respect to partial of xy with respect to x minus partial of 2yz with respect to z plus k times the partial of x with respect to x minus the partial of 2yz with respect to y. And then we can look at our terms. They're going to go to 0 automatically, like this term, because partial of x with respect to z is going to go to 0. Sorry. And yep, that's the only term that goes to 0, sadly. I like it better when more terms go to 0. So this would equal x minus 0 I, minus, this is going to be y minus 2y j plus 1 minus 2z k, which equals xi plus yj plus 1 minus 2zk. Alright, so this is our del cross f. And then we need to do n hat d sigma. Sorry, I forgot that part. And then with our fxyz. So this fxyz is going to be with respect to our surface. So if we go up to here, draw an arrow, goes out. So it's going downward. So that means we're going to have a negative, which would put a negative z. So I'm going to apply 0 equals negative z squared plus x squared plus y squared. Negative z squared plus x squared plus y squared, which makes n hat d sigma. It's going to be del f over, and our projections in the xy, so magnitude of z. So this will equal 2xi plus 2yj minus 2zk. Oh, from a dA here. dA over fz, which is negative. So it's going to end up being 2z since it's a magnitude. And, yeah. Then dA xy. So this will equal x over zi plus y over zj minus k dAxy. So then we have to dot. I believe you have to dot these two together, the n hat d sigma with the dot across f, and make sure that that's what I need to do. Yeah, okay. So when we dot it, we'll multiply each components together and add them up. So with the i's, you'll end up having x squared over z. With the j's, you'll have plus y squared over z. Then minus 1 minus 2z. And then you'll have dAxy. So we need to get all of this in terms to the area variables. So I figured we'll use theta because we're dealing with circles, and with z squared equaling x squared plus y squared. This implies z equals square root of r squared, which equals r. So we said z is equal to r. And we can substitute in for x and y as r squared. So we can do x squared. So we can put x squared and y squared underneath the same radical of z. So it becomes r squared over r minus 1 minus 2r. So I'll go ahead and just substitute that in with r d theta. So this would equal r squared over r minus 1 minus 2, where z is equal to r. So it's r all times by r d theta. Sorry, yeah, r d theta. So then this would equal double integral of r minus, so r squared, so let's multiply that r throughout, minus 2r squared. So I probably plus 2r squared because it's got that distribution, that minus. So it's going to be minus r d theta. I'm going to write the limits out. So for r, it would be from 1 to 2, because when we look at our thing, we go from the inside. We don't start in it. We hit r equal to 1 here. Then we exit r equal to 2 there. So it's going to be from 1 to 2. And then our theta, we just choose 0 to 2 pi. Because this is all about area, so we don't have to worry about the other thing. So yeah, 0 to 2 pi. We start at the positive x-axis and then the positive x-axis. And I'll go ahead and just make this 3r squared minus r. All right, and I'll go ahead and integrate r. So it's going to be from 0 to 2 pi of r to the third minus r squared over 2 from 1 to 2 d theta. This would equal 2 cubed minus 1 cubed minus 1/2 of 2 squared minus 1 squared d theta, which this would equal 7 minus 4 minus 1 over 2, so it would be 3 over 2 d theta. So we can find a common denominator here. So it becomes 14 over 2 minus 3, 11 over 2. Sorry, got distracted. 11 over 2 d theta. Integrate, so we have 11 over 2 times theta. Do theta from 0 to 2 pi, so then we have 11 times 2 pi minus 0. Sorry, 11 over 2, which equals 11 pi. And we got the same thing for the first part and the second part. Therefore, Stoke's theorem is verified. So big thing to remember from here is how to decide your directions. So for the line integrals, it's a big deal because that's what decides your limits and decides whether that's going to be positive or negative, which is a big deal because that gives you your overall answer. And you do this by using the two methods as I said earlier. You know, find the way that makes sense to you in order to find out your direction, or ask for a friend or somebody to help you. I'll be going over this in SI if you need extra help. So yeah, that's pretty much the big thing for this. And remember your problems for this. Remember like what you need to know in order to solve for everything. So your line integrals, it's just f dot dr. For your surface integral, it's del cross f dot n hat d sigma. And remember for your n hat, always make sure you pick the correct surface for it, not the correct surface, like the correct sign for it, so that way your n hat matches up with your like f of x, y, z, so you have the right signs for it. Sorry for all mistakes. I did this one in the other video too. I'm just really tired and just want to sleep and eat. So, hope this really helps. Comment below if you have any questions, or if you have any other questions, you can email me. Hope yourself happy 4th of July and good luck on your tests on Thursday.